In this lesson, we are going to continue working with compound interest questions. However, instead of looking for the future value, what the investment's going to grow to, we're going to look for some different parts. We want to estimate here how long it would take for $1,500 to grow to $25,000 at 8% compounded annually. So what we're missing is the length of time. We know the future value and we know the initial investment. If we look at this formula, our compound interest formula, we know our future value is $25,000. We know we invested $1,500. We know our interest rate is 0.08. It's annually, so divide by 1, it's just 0.08. What we don't know is our time. The other skill we do not have at this point in time is how to solve for that missing exponent. So here is where the graphing technology and the financial application comes in really handy. There is a way that you can solve for exponents, and you can solve for exponents using logarithmic values. We haven't learned about that yet. So in this case, in order to solve for this exponent and to find out how long it takes, we do need to use our graphing calculator. So if we think about all the values that we are looking for, that we are going to substitute into our calculator, here's what we have. N is what we're looking for. We want to know how long it takes. We know our interest rate is 8. Our present value, 1,500. Again, you must enter it in as negative 1,500. Our payment is 0. Future value is 25,000. Pay per year is 1 because it was annually. Compounding period is 1 because it was annually. So if we go to our calculator and we substitute these values in, N is what we're going to look for, so we won't do anything there. I is 8. P is negative 1,500. Our future value is 25,000. And our pay per year and our compounding per year are 1s. So now we can go up and we can find how long this is going to take. And as you can see, it's going to take about 36.6 years. So if you wanted $15,000 to grow to $25,000, and you were only able to find an investment for 8% compounded annually, you would need to leave it for almost 37 years. All right. Jarrett wants to invest $3,000. He has the following investment options. He can do 4.8% compounded annually, monthly, or daily. He's going to invest for 5 years. We want to determine the future value of each investment, but then we want to graph the interest over time for all investments on the same grid. We want to plot at least 5 points for each investment so we can compare the frequency affecting the growth of interest. All right, so we could find our future value for each of these investments simply by plugging the appropriate information into our calculator. However, since we need to find at least 5 points for each investment, we're going to set up a table of values. We are going to have values at the end of a particular year. So end of year values. We are going to have option A, option B, and option C. So our initial investments is $3,000 for all of these. At the end of year 1, we need to find out what our future value is in each case. Now option A, if we are plugging these into the graphing calculator, the N is the value that's going to change from A to B to C and within each particular part. Our interest rate for all of these was 4.8. Our present value for all of these would be negative 3,000. We have a payment of 0. Future value is what we're looking for in all cases. Payment per year, this is going to change. If it's option A, it's going to be 1 because it was annually. If it was option B, it was monthly, so it's going to be 12. And option C was daily, so it's going to be 365. Compounding periods per year, again, depending on whether you are option A, B, or C. Our N for at the end of year 1. For option A, it would simply be 1. For option B, it would be 12 because 12 months in a year. And option C would be 365. So when you find those for the end of year 1, you're going to get $3,144, $3,147.21, $3,147.50. So as you can see, at the end of the first year, putting it in annually, monthly, or daily doesn't make a whole lot of difference. We're talking about just over $3 difference. So not a whole lot if you're just leaving it in for 1 year. If we go to the end of year 2, and we're using our calculators, the only thing that changes is our N value. Option A is going to be 2 because now we're at 2 years. Option B, you would have to change your N to 24. And option C, you would have to change it to 730 because 2 years times your compounding periods. So we are going to get values of $3,294.91, $3,301.65, $3,302.26. So you might start seeing a little bit of a difference here, especially between the annually versus monthly and daily. Monthly and daily are still kind of close together. So let's look what happens after year 3. So again, our ends. Year 3 for annually is just 3. Year 3 for monthly, 3 times 12 would be 36. And year 3 times daily, 3 times 365 would be 1,095. So you'd have to enter those values into your N each time and look for your future value. $3,453.07, $3,463.66, $3,464.62. Again, options B and C are staying relatively close, but option A, where you're compounding annually, is starting to fall behind. It's only $10, but we're only on year 3. Continue this to year 4. Our ends are going to change again. It's going to be 4. 4 times 12 is 48. 4 times 365 is 1460. So options A, B, and C, those are the values you would have to substitute in. $3,618.82, $3,633.62, $3,634.97. Again, B and C are staying fairly close. Option A is starting to fall even further behind now. So here will be our 5th set of points. So year 5, for option A, it's going to be 5. For option B is 60, and for option C is 1825. So hopefully you can see why A is falling so much further behind. We're only compounding it 5 times versus 60 times versus 1,825 times. So the longer you would leave the investment in, the better the chance that C is going to make you more money will occur. $3,792.52, $3,811.92, $3,813.69. All right, so now we've got our points. We can see option C definitely makes the most money. So how does the compounding frequency affect the growth of interest? Well, the more frequent it is compounded, the more interest you are going to make. And we could now graph these. And we're supposed to graph interest over time. So we'll put time along here and interest along this side. And our time is at years 1, 2, 3, 4, and 5. I've spread it out so that we've got some room to look at. And our interest values go from just over $100 up to just over $800. So we can have 100, 200, and we can plot the points. So I'm going to plot option A in black. So at 0 years, they made $0. Year 1, we're just over 100, almost at 100, or we're at 144, 147, oops, sorry. Year 2 was $294, and then it was $453, $618, and then almost 800. So there is option A. We compare it to option B, 3,000 or $0 in the first year, just about the same on first year. Now we start to split a little bit. We're just over the $300 mark. Year 3, we're between $450 and $500. Year 4, just over $633, and then over $800. So a little bit more money. And then if we do option C, we are at a little bit higher than option B. So what you should hopefully see is the more frequent the compound, the more money you will make. Rule of 72 is a simple formula for estimating the doubling time of an investment. 72 is divided by the annual interest rate as a percent to estimate the doubling time of an investment in years. The rule of 72 is most accurate when the interest is compounded annually. So if you wanted to know how long it was going to take to double your investment, so you have $2,000 investment, you want to know how long it's going to take till you have $4,000. You can divide your interest rate by 72, and it will give you an estimation of how long it's going to take in years. If it's compounded annually, this will be more accurate. So if we look at this, Chris invested $5,000 by purchasing Canada Savings bonds. They earn him 9% compounded annually. So we want to estimate the doubling time. We want to know how long it's going to take till he has $10,000. We could then verify our estimate by actually determining the doubling time. So we take our 72 and we divide it by the interest rate, which is 9. What we're saying is in approximately 8 years, he should have $10,000. So we could verify this. We know his future value, we're looking for is $10,000. We know that his principal value is $5,000. We know the interest rate is 9. We know we are looking for the number of years. We know that the payment frequency is 1 and the compounding frequency is 1. So we could substitute those values into our calculator, and what you're going to end up getting is 8.04 years. So it is very close estimation using the rule of 72.